Okay, let's get going today. Just a couple of quick announcements. So most of you have turned in your assignment 3, but I think a few of you had legitimate reasons to turn it in a little late, and that's why the solutions are not up yet. But they will be up, I think, tomorrow sometime in the afternoon. And the next assignment is scheduled to be posted today, and it will be. We had a few days of respite, I hope, and some of you had prelims and all that. So that's so the next assignment is scheduled to be posted today. So, but just to again, as I stated in the last class, we are at the heart of the subject, kind of the middle of the course too, and we're intentionally spending a bit more time at this, trying to understand this, the very important concepts of gain lasing and gain saturation, and today I'll finish up again a little bit of the discussion on amplified spontaneous emission and summarize the whole thing again one more time. And chapter 8 has a lot of problems at the end of the chapter. And some of the assignment problems this time would be a few problems from there, but I mean, I would say that if you do have the time, just try to attempt some of the problems that are even not assigned, because this is kind of the important, one of the most important parts of this course, I would say. So, okay. So that's why we're spending a bit more time here. The other thing I wanted to, I actually forgot last class to just about the exam, and in general, I think most of you do this, but in case you don't, I would kind of encourage you, if you are handling a problem, to go as far analytically as possible with it, with formulas rather than plugging the numbers, because you know that the formulas are much more general. And the numbers are a specific case, right? Now, if you plug in the numbers and you see a negative temperature or something like that, then you know there's something wrong, right? But so you can go back and track back the formulas. You don't have to worry about the numbers. Does that make sense? I mean, I think you get a sense of that, but sometimes we don't do that. But I would encourage you to do that every time. If you're given variables, even if you're not given variables, say, oh, the size of the cavity is 50 centimeters. Say D is equal to 50 centimeters and go with D first, and then later on you substitute it. That if you just use that sort of an approach, you will generally it cuts down the work by a lot too. So yeah. Okay. So I want to get back to discussion of a few remaining topics of chapter, and I can use the board initially, and then we go back there of chapter 8. And I was trying to also in the last class go back to the very basics, and within 2 or 3 steps we arrive at the main laser equations, because once the concepts are clear, then you the reason I'm saying this is many times there's a lot of confusion because there's so many variables. Some of them are repeated 5 times in radius of curvature, reflection coefficient, all that stuff, right? And so there's gamma, which is the gain, and there's nu, which is the frequency, but they look somewhat similar and all that sort of thing. But once you get the physical feel for what they are, I think hopefully that confusion will melt away. So one more time, we're going to go back and say what I want to do is motivate what is amplified spontaneous emission, and actually Cliff has already mentioned that mentioned it in the class last Friday, and I was just about getting started on it in the last class, but I will discuss this now. Okay? So I want to motivate amplified spontaneous emission, but we're going to go back and say that what if I had essentially if I just had a gain medium, a medium with atoms, and then I'm pumping it either optically or electrically, whichever way I'm pumping it, and but there are no mirrors. There's no cavity. There's no cavity in there. So so what happens? Can there be gain? And the answer is, of course, there can be gain. The moment you create stimulated population inversion, there'll always be gain. Right? Now, whether you feed it back into the cavity, create an oscillator, that's up to you, right? But the gain will be there, right? And that's this idea of amplified spontaneous emission. And what do you have gain in? Basically in the spontaneous emission. You know, whatever light comes out because of spontaneous emission will be amplified. You know? And it can be useful and it can hurt. So if you are trying to make a laser with one frequency, it will hurt you because that will eat away your, it will be an issue. But for some other applications, and I'll mention one of them, which are called where you do not want coherent light, you want incoherent light. Sometimes you do. And there it's actually useful, the amplified spontaneous emission. And in semiconductor industry, for example, there's a particular kind of diode called the superluminescent LED or superluminescent light emitting diode, SLEDs, SLEDs, where it's used. You know, this amplified spontaneous emission is used. So let's see what that is. So essentially, the basic question we're going to ask is kind of generalize this problem and say that, well, you know, if I had, say, NP number of photons inside any region, then, or actually, let's not say that. You know, I'm going to just consider the atoms inside have, say, 2 levels, 1 and 2. And again, just like we have done before, there is a spontaneous emission rate of A to 1 and a stimulated emission rate of B to 1. Right? These are the Einstein A, B coefficients. And just based on that, what I can write down is the rate of change of the number of atoms, or you know, rate of change of the number of occupied states in state 2 is equal to, so a decrease because of spontaneous emission, right, and a decrease because of stimulated emission. It's very simple, right? Decrease because of spontaneous and a decrease because of the stimulated emission, and the decrease because of the spontaneous is A21 times N2, right? That we know very well now by now. And these are things we should really lock in the mind, meaning I shouldn't have to open the book to write this, you know. And I hope most of you get to this stage if you haven't already. So, and the second is now I know that, and if you remember, Cliff had really described it beautifully, saying that the stimulated emission obviously depends on your population inversion. If you don't have population inversion, there's no stimulated emission, right? So that immediately tells you that is proportional to N2 minus N1. But then there are these, you know, finicky degeneracy factors. We just add them in. You know, don't have to remember this thing, but if the degeneracies of state 2 and state 1 are 1 each, then it's just N2 minus N1. So that's your population inversion, right? And that's how many atoms are population inverted. And the picture that, if you remember, Cliff gave you is, you know, these are basically like doves, and we're shooting, or rather, so this is kind of the, if you think of it as number of bullets that you're shooting, and the number of, you know, such changes that, or such decays that can happen are population inversion times a cross section. Then, you know, the rate at which, or the number of such things available times the cross section area of each, right? And then that is your that, you know, you can call it the stimulated emission cross section, or whichever way you like it, and that is related to A21, and it's given by lambda square by 8 pi n squared, and it includes the line shape G of nu being frequency. These are all frequency dependent, all frequency dependent. So it's a spectrum, right? And this is your line shape, and does that make sense? I mean, that's your whole picture. So it's essentially that's your stimulated emission rate, and then so I just put that in there. N2 minus G2 over G1 times N1, right? So that's your rate equation for any such process. You know, it's just, this is a 2-level process. And later, we're going to see what happens if you 3 levels, 4 levels. No problem. All you need to do is keep track of all possible changes. You know, down, up, add them all up. They should all be, you know, consistent. That's a standard rate equation. And so that's the rate equation for the number of atoms in state 2 and state 1. They are obviously related, right? And I think when you kind of reach lasing or kind of are building up towards lasing, I think you know that some of the tricks you play are say that, well, N2 is very large, N1 is very small. It's kind of all the atoms are stimulated, population inverted. That there, you know, and you can kind of use some of these tricks to find out what would be the timed evolution of these states and such and such things. You can kind of find those things out. So that's the number of atoms. Now we are typically also interested in power or intensity of light that is emitted if you have a laser or whatever case. Here we are not yet talking about the laser, but the intensity of light would be, first of all, is that clear? I mean, this hopefully, I'm just probably maybe the 10th time we are talking about this here, but you can, so there's a spontaneous part and there's a stimulated part, and both of them essentially decay the population. And later, a little bit later on today, we'll see that the maximum. Well, let me write it down now. The intensity of light is given by the number of photons per. Intensity is in units of watts per centimeter square, watts per unit area, right? So the amount of power delivered per unit area, and that I think you can right away see it should be N2 related to because the number of photons that will come out will be proportional to N2, the number of population inverted states that are available. It will be proportional to the photon energy and times the number of population inverted terms. So that would be kind of a measure of the intensity. But what I wanted to kind of say is there is another relation between intensity and the energy density of radiation, right? So if you have a frequency and you say in this frequency range I have this much energy or this much power in watts, this is where we started this whole discussion with black body radiation. I know this is the radiation pattern or the radiation spectrum, and that is in watts per centimeter cube, and frequency per hertz, right? Per hertz, if you want, or can have the second in the numerator. So that's and then the intensity as a function of frequency is this, and you do see speed of light over kind of the refractive index, the group velocity refractive index. I mean, and for many practical cases for us is 1, but it's something like that, right? And that converts this into watts per centimeter square, and you get the speed of light involved there. And what I want to get to is, if I want to, instead of tracking number of atoms, if I want to track intensity of light, this is really what I'm after right now. The intensity, how does it change of intensity of photons as I go along in Z, from say here to there as I'm pumping it? How does the intensity change, right? And that is given by, again, there's a part because of spontaneous, and there's a part because of the stimulated emission, right? The intensity is changing because here I have some of these atoms that are spontaneously emitting, but the spontaneous emission part is going in all directions. It's going in all directions, right? So let's write that down. How do I write all directions? All directions will be represented by an angle, solid angle over 4 pi. What does that mean? If I want to find the intensity, let's say this is my 0, and I draw a very big, like a sphere, and what would physically be called an integrating sphere. So you place this thing inside a big sphere, and I go out here and say that, well, how much of my spontaneous emission is coming out in this little window here if I put a detector there, right? Inside, physically, this is, say, your laser gain medium, and then you place this whole thing inside a big sphere, and your detector is kind of sitting here, and say how much light is coming out here, right? So that extends a solid angle, which is a part of the whole sphere, right? And that's what we mean. I think so there'll be a solid angle here with a little curvature, and then if you integrate it over the whole sphere, you get a 4 pi, right? But this angle here, we are saying that's d omega, and then it's just some fraction of the whole thing. Because spontaneous emission is going in all directions, no matter where you are spontaneously emitting from. It's going in all directions. Everything that kind of spontaneously emits inside the gain medium here is going to make it there, right? So that's the part. And what is how much is going to be emitted? Well, I think we know all that. A21 from spontaneous emission here, right? And so I'm basically, and each photon N2, if there's N2 remember is not the number but the density. So if the density here is N2, also here, inside the entire material, the densities of these atoms which are giving you stimulus is constant. N2 H nu is the photon energy. Remember we are talking about intensity, so I must have the energy here now. And the shape, this factor always appears, and I hope we are clear, the line shape, because if all the light was going into only one frequency, or rather every atom has its own propensity to emit at different frequencies, and that's really what we are calling as the line shape, and it's always there. Right? So, yeah.
If the atoms are going in all different directions, why do we use the A21 rate?
So let's see. You are asking if the atoms are going in different directions.
You said for spontaneous emission, they're going in all different directions.
Yeah. So the light is right. So the atoms, you can imagine, we're not talking about the Doppler shift and all that, where atoms are actually moving. Let's say a solid state laser where the atoms are fixed to the lattice, but the light, spontaneous emitted light, is going in all directions. It has no preference over should I go this way or that way. It goes in all directions, and that's why we have this factor. Meaning, each little patch on this big spherical ball has equal probability. The probability of receiving, say, 10 photons here, number of photons is proportional to the total number of photons that are coming out divided by the area this area divided by the whole area, in some sense, and that's what we're saying here. And this is essentially the rate at which the photons are coming, the total number over the whole thing. Does that make sense? And here what I'm doing is really not the total intensity, but just the rate of change, meaning if I go from Z to Z plus dZ and say how much, treat this as my light source and say that from here how much light is going there. Does that make sense? From that little slice. And then if you want to find the total intensity, you integrate from 0 to Z, 0 to L, whatever is the length of it. Because that's your light source here, right? The whole thing. Does that make sense? I don't know whether I answered your question though. So
for A21, that rate is the atoms that are going to a lower state, but the light is being released in all directions.
Correct. So there are N2 number of atoms per unit volume here, and each atom emits at a rate of A21. That's the spontaneous emission rate, each atom. And so each atom is emitting at this rate. This is the number of atoms, right? So, and this is the photon energy of each photon that is emitted. And this is the line shape, which says that, because of the medium, it has a certain propensity to emit at a certain frequency more than some other frequencies and so on. It could be sharp, depends on the problem. And this is the area argument, saying that it's equal. Spontaneous emission is going equally in all directions.
And does it matter that we're doing like a circle speed, or like should we be doing like a spherical?
So because spontaneous emission, let me just explain perhaps this term a little bit more. So if I have an atom which is in an excited state, and I really have a physical sphere, and I'm trying to detect, I have all kinds of detectors. Let's say, well, in the granular level, photons are discrete objects at the quantum level. So I have detectors all around, and I'm looking for, if there's only one atom, only one of these detectors will click and say, well, the photon came out here. There'll be only one. So there's no such thing as a uniform thing. But if I do it again and again, so if I'm continuously pumping it, and every nanosecond it's emitting another photon now. So over time, as I detect it, and I'll see if I plot as a function of angle here, what is the photon count that's coming out, let's say, right? you'll see that initially you'll start like that. There's only one when it came out. That's quantum mechanics. Then you do one more like that, one more, and then as you go, increase time, so essentially it will flatten out completely. And what is this value here? This is d omega over 4 pi. And the reason the light has no preference in emitting in any direction is because it's really not in a cavity. It's spontaneous emission. I mean, it doesn't. But once you put in a cavity, it forces it. It increases the probability of going. If I put the atoms now in a cavity like that, let's say, optical cavity. Now the emission probability is more peaked in this direction. So instead of this thing, it's going to. That's stimulated part. But the spontaneous will always stay. It's not going to go away. So, does that make sense? I mean, now these two compete. Spontaneous and stimulation compete. How do they compete? Right here. These coefficients will tell you how they compete. Right? Does that make sense? Okay. So that's your spontaneous part, and the stimulated part so that's how much intensity is increasing over any frequency range with Z. And the stimulated emission part, I think, is pretty clear. We know now that that's just the gain at frequency nu times intensity at Z, comma nu. Yeah. So that's your equation of how the intensity is changing with Z. And let's say we're looking at, so the light can go to the right here inside this medium and can go to the left. And I'm going to just sketch how might the right going wave look. And so as we are pumping it and you're creating stimulated inversion inside, population inversion inside. So I think you can see right away that on the leftmost side, if I'm just looking at the right going intensity wave, or the intensity of the right going light wave, let's say plus is right going, plus. Notice that the spontaneous emission part does not care about what is your intensity because it's spontaneous. It doesn't care about how much light is already there. Spontaneous emission. Stimulated part heavily depends on it. It's proportional to it, right? That's the meaning of stimulated emission. What is the proportionality constant? That's your gain coefficient of the laser. I think your book is using what? Gamma naught. Okay, gamma naught. Fine. And gamma naught, what is gamma naught? It's basically the product here. The gamma naught is gamma naught as a function of frequency nu is your cross section, absorption cross section times the N2 minus N1 G2 over G1. I mean, I think you've kind of seen that. And what is sigma? Well, it's cross section is that. So that's your whole story here. And this one you can measure directly, spontaneous emission lifetime. Kind of at t is equal to 0, turn off your optical source and say how is this spontaneously emitted light decaying with time. Find the exponential, find tau2, get your A21. A21 is basically tau2, it's the rate. So once you know this, your wavelength, the line shape, all of that, you have the whole problem, essentially solved now. So that's your the kind of the it's not the rate equation here, but how is light changing in space, spatial variation. And I think it's, let me just say that this is a rather straightforward thing to solve with, okay, so I can see this is my variable here. D nu's go away, frequencies, so there should be a D nu somewhere I missed, yeah. The frequency range, they will go away. And then you can solve this. This is your variable, intensity as a function of Z, intensity as a function of Z. Solve it, and you get something very kind of illustrative, I would say. And it will explain this idea of amplified spontaneous emission. Let's write it as a function of nu, right? And I'm not going to, basically you can see these coefficients will kind of fall out here. It's a very standard equation like d over dz of, let's say, f is equal to some constant plus f times another constant. It's a very standard linear equation, right? But I think right away you can see that if you turn off the spontaneous emission part, this part, di by dz is equal to I, so it's an exponential function right there. You can see it right there. It's an exponential function. And how does it look? I'm not going to kind of go through this, but I think I'm not going to hold derivation, but there's this A to 1, and you can relate all that to your cross section and all that stuff. You can observe it in exchange, trade off your A to 1 for your absorption cross section. And after you do all that stuff, what you will end up getting here is this formula. Let me just write that down. 8 pi n squared over c squared over h nu squared times n2. Again, I mean, I hope you can see all this just falls out there, and times e to the power gain times the length of the cavity, if you want to look at the length, or at any z. All right. Times frequency times any z minus 1 e to the power this thing minus 1, and that's what you're going to get now. So that's your intensity spectrum. Oh, and then where is this intensity in any of these little windows? I want to detect it. I put a detector on a little window out here and say how much watts per centimeter square is incident on this window. That's what we are kind of writing down here. And so this is actually very interesting. If you look at it a little carefully, what you realize is it has so this is your gain term. Gain is e to the power gamma naught times the length of whatever is the gain medium. Remember, gain medium is only here, not here. Out here is outside the gain medium. So only this length appears in your gain, not the whole cavity or whatever distance you are going out to. It doesn't appear there. So that's your gain medium, and h nu cubed. I think I should have h nu cubed over c squared. Right. So this is your spectrum, no mirrors, just amplified spontaneous emission. It's the intensity profile. And this is essentially what did we plot here. As you go to the right, your intensity is increasing, and then the intensity of light is increasing because you had your spontaneous emission part, which is your noise, but because you have population inversion, you have an additional stimulated emission here, which is the light is gaining strength as it goes to the right. Does that make sense? That's so you're amplifying spontaneous emission, and spontaneous emission is kind of this background thing that's going on here, which is just that. That doesn't depend on the intensity. Make sense? So the light is gaining strength as you go to the right. And by this time, I mean, this is what we are plotting here. Sorry, this is what we are writing here. This is kind of your e to the power z minus 1 and all that. And here's your population inversion and all that stuff. And if you look at it, it looks very familiar. And I mean, for obvious reasons, actually, as you would imagine right now. So this is just for the right-going wave. Similarly, there'll be a left-going wave which will also grow, as you can see, right? And essentially, what will come out from here would be a light which is not a laser, but it has it has amplified spontaneous emission. That has characteristics of the spectrum, has the characteristics of the material that you have inside here, and the pump. Right? So now, if your population N2 and N1 was not, so actually it turns out that this derivation does not require your gain medium to be under population inversion. It's valid for all cases, even if you don't have population inversion. Yes, I mean N2 and N1. It doesn't have to be. It's not limited to that. And you can go back and ask, what would it be if my population was thermally distributed, meaning it was not inverted at all, but it was just normal thermal distribution, thermodynamic equilibrium, right? The opposite of population inversion. And that you can plug in here, and what you'll recover is something again very familiar, and that is a conformation of h nu cubed 1 over h nu over kt minus 1 And that will give you like a 1 minus e to the power minus. Let me just write that down first, and I can discuss briefly what that would mean, right? By 4 pi. Yeah. So essentially, if you just plop this thing in here, you recover that the spontaneous emission. Remember, when you do not have population inversion, this is a spontaneous emission, right? And the spontaneous emission spectrum, if you look at this term looks like very much like not very much like, this is exactly, this is an old friend. This is your black body radiation, Planck's black body radiation formula, and then there is a little bit here which is kind of the loss, because when there is no gain there is loss, right? So as you went across a little distance, if you think of this as your gamma naught as your gain, then if your gamma naught is negative, which it will be if it's thermal, right? Gamma naught would be slightly negative. That means there's a little bit of loss. How much of light do you lose when moving through a distance L? Well, it's gamma naught times the length of that gain medium. Right? Is that how much? This is typically very small, not much, but essentially it's saying that you can only emit from this. If you pump it and you do not create population inversion, your emission spectrum is going to look like the black body radiation spectrum. So, and this is actually kind of a very interesting thing. It's called Kirchhoff's law, which says that if you don't pull a system out of equilibrium, if it is in equilibrium with the light and all that it's exciting, then the maximum amount of light it's going to emit is also equal to the light it absorbs. It's a reciprocal process, and this is related to emissivity of materials and so on. Just a kind of a side note here, but it's kind of interesting, I think. Yeah. So you recover, and there's no magic here. Essentially, we started from this and we ended up here, really, in some sense. I mean, and then just confirming that everything is right. The other part of the amplified spontaneous emission is as I mentioned, if, for example, in semiconductor lasers, sometimes we don't want amplified spontaneous emission. Sometimes we just want to do the following. And here's some of the places where some engineering or design comes in, right? So let's say I make a semiconductor, or sometimes not necessarily a semiconductor, but I take a typical semiconductor light emitting structure. And we will talk about this in much greater detail later. But essentially, what you have in a semiconductor light emitting structure is a structure that would look something like that. So essentially, this layer here, these will be layered materials grown by typically epitaxial processes, molecular beam epitaxy or MOCVD or such techniques. So here you will have a P-type semiconductor with holes, N-type semiconductor with electrons. You inject holes, inject electrons, and then inside this little region you try to create population inversion inside that little region. And we'll discuss this in much greater detail later. But what I'm trying to say now is if you want to make a laser, what you do is you take this and you will kind of make this very long in one direction. And it's be a waveguide. So essentially all the light that comes out will kind of bounce back and forth. And then this end of it would be a mirror. It will kind of cleave it. It would be a mirror. It will turn the light back again. So that's your mirror, R1 reflectivity, let's say. And then the other side there will be R2. So the light will kind of go back and forth and between the two mirrors. And then this region is your gain medium. Why? Because you have created population inversion. N2 minus N1 is greater than 0 here. So that's your gain medium. So as light goes back, it increases, and then I think you know that it will reach a certain threshold as you start. So the way you reach the population inversion is inject more and more current, and then you kind of drive it harder. That's the pumping, electrical injection pumping. And so if the mirrors have good reflectivities, then obviously the light will go back and it reflect. And finally, what you do is sometimes people add these distributed Bragg mirrors and all that sort of thing here to make sure the reflectivity is very high, close to 1. And one of the other sides would be smaller, maybe 0.9 or 0.8 or something like that. And then the light would kind of come out from here as a laser beam, right? So that's how typically it would be made. And we're going to go through it. We'll calculate quite a few things. We'll design a few things later in the class, maybe I think next month in November. or late October, something like that. So, but sometimes, as I was saying, one does not want the laser beam. What did you do here with the cavity design? The LED itself, meaning the device itself without these cavities, if you just measured the luminescence when you inject the current, let's say it was looking something like that, wavelength or frequency. Let's say it's a green laser, which LED, so that's maybe 530 nanometers, and you look at how much light is coming out far away somewhere, it will look something like that. That's how the semiconductor, this active region, is going to emit. It's been designed. The material composition, all that has been designed to emit there. Now you build this cavity, put this mirror, and then maybe another mirror on this side, and with a 90% reflection and 100% on that side. What do? You create your FSR right away. It's a cavity, right? You have only these modes allowed now, right? These are the modes allowed, and now when the light is emitted, it will emit into one of these modes. That's the idea, right? Because or it will try to emit into other modes, but they don't fit inside this box, right? And so it's unable to, so it's going to start emitting into these modes now. So essentially the spectrum will this part will go down, and this part will grow, this part will go down, this part will grow, and does that make sense? I mean, the spectrum is going to start looking like that now. Okay. And then you inject more current, and at some point, as you know, your gain overcomes the loss, and it locks into one of the modes, the mode that has the highest gain, and you get the laser. That's the idea. So, and that's the threshold current. You get the laser at that wavelength, right? Now, sometimes, as I was saying, you don't want to do that. You don't want it to form this sort of thing. You want it to, you want to do is you want to make the full width half max smaller, and you want more light you want to reshape this function, the emission spectrum. You want to do something maybe like that. You don't want a laser mode, but you want something like that. Let's say you want to decrease the full width half max, make it more spectrally coherent. So how do you do it? I think you can see that you don't want the cavity modes, right? You don't want the cavity modes like that. And a nice way to look at it is if you look at light, that may propagate in this way. This is clearly if you have, the k vector or the propagation direction is perpendicular to the mirror surface, you will have reflection, so you'll have cavity modes. But if you just change the shape a little bit, like that, let's say, then you will have very low, very, very low reflection. In fact, none almost. I mean, there'll be always a little bit, but you make sure that the light just goes out. It doesn't stay in after a single pass. So essentially, you get your amplified spontaneous emission, get out. Get your amplified spontaneous emission and get out, and don't stay inside. So that's basically a kind of a laser without a cavity. But you need that, and it's useful for quite a few things, optical gyroscopes and that sort of thing. Some medical applications as well, so you can do that too. That's a use of amplified spontaneous emission. Okay, and we are going to come back to the semiconductor part in some detail, and perhaps I'll give you a little problem where you can calculate, as you know, the light, so there will be gain in this. It's not a laser, but there's gain. There's gain in a certain frequencies of light or certain wavelengths. So that's kind of the interesting thing here. So, in other words, the area here is kind of the same, but you're reshaping it, and there is increased photons in some region and decrease in the other. Okay, so the full width half max of this spectrum is going to decrease, and you can kind of show that as well, because there's gain, there's a reduction. So this would be the normal spectrum, let's say, and then once you have amplified spontaneous emission, the FWHM shrinks. And obviously in a laser it shrinks as well, but it goes very narrow. Okay, so okay, so the last thing, this is kind of, I like this picture to have the whole story in one slide, the whole thing about the laser in one slide. And this is last part of chapter 8. So, and it says a laser oscillation from a different perspective. Please read that, because it's actually very illuminating once you have seen all the gory details. The fact they're trying to highlight there is actually to understand the laser oscillation. You could have skipped a lot of the details, because but this is, in retrospect, it's simpler, not when you don't know it, right? So here's the picture now. So again, you have now we put our mirrors back, and you have a gain medium. and you ask the question, well, how many photons are coming out per unit time or being emitted at unit time inside this whole volume, let's say, the whole volume inside here. And that's, again, the spontaneous emission, number of photon, the decrease of the number of excited states, right? So we just did it. N2 is the number of atoms in the higher state, and they're going to all decay at this rate. And every time N2 decays, you create one photon, right? So that's why we have this, right? And that's and the volume is V. So this is not the density of photons, but it's the number, like 10 to the power 5. There's no units for that. It's the number of photons. So the number of photon increase is number of atoms which have are excited and can spontaneously emit times the volume times the coefficient. So that's really very straightforward, right? That's the total number of photons that are created. But because you are inside a cavity, when you are talking about a laser, because you're inside a cavity with a FSR, right? It's not going to be able to emit into all modes. There are only a certain restricted number of modes which it will be able to emit into spontaneously, not stimulated, spontaneously. What are those modes? Well, that's where there is the nature of the atoms, and then you have a FSR. FSR tells you that the bandwidth is delta nu, and we know that what it is. It's 2 times C over 2nd. That's very straightforward. Inside your cavity like that, if this is D, right, the distance between the mirrors is D, then this is the number of modes, in some sense, it can potentially emit into, right? Does that make sense? These are all the allowed modes now, all of them, right? Right? But I don't want to know what happens to all the other modes because they are going to just die, right? I just want to know what happens to that particular mode which is going to survive when the laser oscillates, right? Right? And what fraction of the total number of modes is that? Well, that's very straightforward. Again, it's just one mode out of the total photon density of states. How many photons are there? And that we have kind of written down 8 pi n squared. What is it? C cubed nu squared. And then again, times d nu, which is your frequency range, and that's actually C over 2nd. This is the volume density, frequency, volume and frequency density. Remember, this is 1 over volume times frequency, or frequency window. That's your photon density of states. This is the frequency window over which you are looking at, and finally the volume must also appear. So that's your total rate of change of photons due to spontaneous emission, the whole thing. And then your volume and volume just go away, FSR go away, and you're left with something much simpler, which depends on the line shape and all. So that's your spontaneous emission, and you can reclub it all and write it very nicely in N2 times the speed of light times your cross section that we have talked about earlier. And the cross section is just what we have, written in the last thing here. You can see this just emerges by this combination of here and here. They just combine and give you that process. And physically it makes sense. Number of photon increase is the number of atoms that can emit and give you photon increase because spontaneous emission, the speed at which they're moving, and the cross section. So very simple. And sometimes it's written as spontaneous emission cross section SE, but same thing. It's okay. So that's your spontaneous emission. And we know now, just from that discussion, that's not the end of the story, because if you have a gain medium, there's a chance of stimulated emission now, right? So we add that. And stimulated emission is actually even simpler. You don't have to even, think about too hard, because I think Cliff gave you a very nice way to look at it. If you have a blob of photons here, say NP photons, right? NP number of photons here, and then you go this way, come back here. What is the number left? Right? Has it changed? If it has changed, the rate of change, I can write it down inside the cavity after one round trip. Right? So if I started with NP photons here, and I went it this way and came back, reflection coefficient R1, R2, and gain is G inside this, which is basically e to the power gamma nu times L and all that. I think you know that now, right? Gain is this. So photons going through this medium, if there's gain, it increases in number, then loses a little bit here, comes back, increases again in the gain medium. Let's say this is the gain medium, and that's LG. Let's say, or the whole thing is maybe a gain medium. But I think it's pretty clear that the rate of change of number of photons due to stimulated emission will be equal to, so we started with NP, right? Started with NP number of photons, maybe 10 to the power 10, whichever be it, or even 5, and then went through there, did a full round trip. I think you know that after a full round trip you have 2 gains because you have 2 rounds. And then you have one loss on the left, one loss on the right, right? And that's the change in the number of photons, G squared times R1 R2. Right? So that's the number that has come back, right? Then what's the change? You started with NP, so NP minus that. That's really the change, right? In the number of photons. And how much time did it take? Well, that we are pretty clear now. 2ND over. Is that right? Did I write that? Yeah, that's the time it took you, right? So I think I was probably writing FSRC. So I think D over the inverse of is the frequency range. So I might have just. No, I think I did it correctly. See? That's nice. Okay, fine. It's just all right. So and here you can see you can take that common out, and that's your stimulated emission rate. Right? Yeah.
When we're talking about NP, we're only talking about one particular point in the cavity, right?
Correct.
So it's not like it's a uniform.
Not at all. Exactly right. So you go to some place in Z, sit there, and say how much NP is here, right? But the thing is, you're right. So and it will. Once things reach steady state, it essentially becomes uniform after that, right? In reality, you form these blobs of standing waves, so you'll be more NP here and less NP here in reality. But right, you're right. NP is variable with Z, but the result we're getting is going to be independent of it. Meaning it's a general result. So, yeah. Right, good point here. And then essentially now the total rate of change of the number of photons is what we are after, and that is essentially just a sum of the stimulated and spontaneous, as we have written many times by now. And when you do that, total therefore will be N2 times sigma cross section times speed of light plus all the stimulated part, which is G squared R1 R2 minus 1 over 2ND over C, right, times NP. So again, you got your rate equation now. Here's what we do not know. And in a sense, we do not know this as well. But I think we'll see now that we now ask so this is a rate equation. You got to solve it. It has all the physics of the laser in it now. Right? Entire physics of the laser. So that's that. And I think you realize right away here is by looking at just this, if my gain term, this term is larger than 1, so this is positive, so that NP basically that's going to grow, right? NP is going to grow exponentially, right? And if you do a quick estimate of this term, which is your spontaneous part, and this is stimulated, right? Let's do a quick estimation. N2 10 to the power 12 centimeters square, a very high cross section. So we are looking at the high end, how much, max value. What am I doing? 10 to the power, sigma. The cross section is 10 to the power 12. The number of atoms, we are also 10 to the power minus 12. Is that okay? This is the cross section. I think you've seen that. Number of atoms, let's say we have a gas, 10 to the power 12 per centimeter cube. And speed of light, straightforward, 3 10 to the power 10 centimeters per second. So you get some numbers like that. Estimate the number of photons, but I want to know the power because I'm calibrated with power. I want to know how much watts is there because of the spontaneous emission term here under these conditions. And let's say each photon, let's see, so first of all, these cancel. So you're kind of looking at about 10 to the power 10 centimeters square. and centimeter cube and centimeter cancel. So essentially you're looking at the rate of change of number of photons is 10 to the power 10 per second. And let's say each photon, I'm looking at a close to 1.55 micron laser, which is the telecom wavelength, and that is about 1 electron volt, let's say, 1 eV. So 1 eV is going to carry, h nu would be 10 to the power minus 19 times basically electron charge joules over eV, right? So that's how much power you're going to get from the spontaneous term. How much is that? Well, forget about 1.6. Joule per second is watts. Right? So essentially we are looking at a nanowatt, 10 to the power minus 9 watts. Very small, nothing almost, it's negligible. But it's extremely important to get the laser oscillation going, to start the oscillation, because you need those little photons to get into that mode first, right, which is going to oscillate. And then. But this term obviously going to grow exponentially, and it's going to grow very fast. And because essentially your number of photons at time t is number of photons at time 0 times e to the power g squared r1 r2 minus 1 over all that stuff. It's time. So if this is even slightly larger than 1, I think you know that it will grow exponentially e to the power a positive number now. It's going to grow very fast. I think Cliff gave you a nice example of how many passes do you need to get to like 10 to the power something, very large number, and it's not too many. I mean, you go there fast. So once you build up the gain, and it's going to grow very fast, this term is going to completely overwhelm this term, and you can now get into terms which instead of nanowatts, we're going to be looking at milliwatts and all that. 10 to the power 6. This term is going to win. Right? But at the same time, I think, as you know, N2 is changing. I mean, things are changing all the time because it's a dynamic process. You started with no N2 and all that. And once you reach steady state, you look at it and it's very weird, but true, that the steady state, this is 0, obviously. So therefore, this must be equal to that. Right? Sorry, it must be equal to that. And this thing is always positive, spontaneous emission part. Right? It's always positive. Therefore, this must be negative. There's no way around it. Must be negative. Okay. So that looks a little weird, but this is where this idea of remember, if that's your gain spectrum, gamma naught of z, gamma naught of nu, and you have your FSR and all that. Remember, once you laze, you lock into the highest frequency, but your gain becomes just slightly lower than the loss. It kind of pulls the whole thing down. So. And the gain spectrum is pulled down, and that's what it's saying. And you can calculate now what is your gain GS, the saturated gain. You can calculate it, very trivial. Just put the two terms equal to each other, right? And you have everything else, output power, photon energy, reflection coefficients, all that stuff. You get your gain spectrum, saturated gain right away. And you get like 1.066 or something like that, depending on the structure. This was how the laser was first, really. And you can take this and say, here's my mirror. You can find line widths and all that stuff. This is how Shallow and the first some of the first derivations of laser line widths and all were done this way. And then it's kind of nice to. So it's all somewhat simpler almost, but it has the same physics. Okay, so I'm going to kind of leave that topic here, and I think in the next class we're going to. Cliff is going to get started. So that's complete chapter 8. We'll have the assignment. In the next class, we're going to get started on chapter 9, where we will talk about quantum efficiencies and all that of lasers, see what sort of laser is good, 4 level, 5 level. But I just want to say that once you understand one rate equation, you understand all of them, right? And all these efficiencies, pumping efficiencies, quantum efficiencies, pumping efficiency specifically, which is kind of the most difficult part to understand sometimes, is just a bunch of rate equations. If you have N3, you're populating it this way, N2, you're populating it from top, and so on, and you write all those equations down, then the total number of atoms in 0, 1, 2, 3 is the same. The rates must go to 0, so you get steady state, just like we did just now. And all the details of it, small signal gain and all will come out from here, no matter whether you have 10 level system, 5 level, you have, rate equations just like what we did for the 2 level today. So, okay, good. So we can finish the discussion today, and we'll meet again Monday, and Cliff will start chapter 9. So if you want to read about that.